Welcome to our video on correlation analysis. Correlation is a statistical measure that helps us understand the relationship between two variables. In this video, we'll explore what correlation is, how to calculate it, and how to interpret it with a worked example. Let's begin by understanding what correlation means. Correlation measures the strength and direction of a linear relationship between two quantitative variables, which we'll call x and y. The Pearson correlation coefficient, denoted by R, always lies between -1 and +1. Let me show you visually what different correlation values look like. A correlation close to +1 means there's a strong positive relationship, where both variables increase together. A correlation near 0 means there's little to no linear relationship between the variables. And a correlation close to -1 indicates a strong negative relationship, where one variable increases as the other decreases. Now, let's look at how to calculate the Pearson correlation coefficient. The formula for the correlation coefficient R equals the sum of the products of x minus x bar and y minus y bar, divided by the square root of the sum of x minus x bar squared times the sum of y minus y bar squared. In this formula, x bar and y bar represent the means of the x and y values respectively. The numerator measures how x and y vary together, while the denominator normalizes the result to ensure it falls between -1 and +1. Let's break down the steps to calculate the correlation coefficient. Step 1. Calculate the means of the x and y values. Step 2. Find the deviations by subtracting the mean from each value. Step 3. Multiply the x and y deviations for each pair. Step 4. Square each of the x and y deviations. Step 5. Sum up all products and squared values. Step 6. Apply the formula to find R. Now, let's work through a complete example to see how correlation analysis works in practice. Suppose we have 5 paired observations of x and y values as shown in this table. We want to find out if there's a correlation between these variables and how strong it is. Step 1. Let's calculate the means of our x and y values. The mean of x, or x bar, equals the sum of all x values divided by the number of values. That's 1 plus 2 plus 3 plus 4 plus 5, divided by 5, which equals 3. Similarly, the mean of y, or y bar, equals 2 plus 3 plus 5 plus 7 plus 11, divided by 5, which equals 28 divided by 5, or 5.6. Step 2. Now we need to calculate the deviations from the means. For each value, we subtract the mean to find how far it is from the average. For the x values, we subtract 3 from each value. For the y values, we subtract 5.6 from each value. We also calculate the product of these deviations and square each deviation, as these will be needed for our correlation formula. Steps 3 and 4. Now, we need to calculate the sums needed for our formula. First, we sum the products of the deviations. 7.2 plus 2.6 plus 0 plus 1.4 plus 10.8 equals 22. Next, we sum the squared x deviations. For plus 1 plus 0 plus 1 plus 4 equals 10. And finally, we sum the squared y deviations. 12.96 plus 6.76 plus 0.36 plus 1.96 plus 29.16 equals 51.2. Step 5. Now we can apply the correlation formula using our calculated values. R equals the sum of the products of deviations, which is 22, divided by the square root of the sum of squared x deviations, which is 10, multiplied by the square root of the sum of squared y deviations, which is 51.2. This gives us 22 divided by the square root of 512, which equals 22 divided by 22.627, approximately 0.973. Step 6. Finally, we interpret our result. A correlation coefficient of approximately 0.973 indicates a very strong positive linear relationship between our variables. As we can see from our scatter plot, the points form an almost perfect line with a positive slope, confirming our calculated R value. Before we conclude, there are some important things to keep in mind when using correlation analysis. First, correlation only measures linear relationships. It may miss nonlinear patterns. Second, correlation does not imply causation. Just because two variables are correlated doesn't mean one causes the other. Third, correlation can be sensitive to outliers, so check your data carefully. And finally, correlation works best with normally distributed data. In conclusion, correlation analysis is a powerful tool for understanding the relationship between two variables. We've learned how to calculate the Pearson correlation coefficient and interpret its value. Remember that a value close to +1 indicates a strong positive relationship, a value close to -1 indicates a strong negative relationship, and a value near 0 suggests little to no linear relationship. Thank you for watching. I hope this video has helped you understand correlation analysis and how to apply it.